Hello, everyone. My name is Frans van Die, and today I'm going to present our recent work on the detection prospects for the gravitational wave background of a galactic population of primordial black holes, mostly for the LISA experiment. And we're mostly interested in subsolar mass black holes, as these are a primary indicator of a possible primordial origin of these black holes. Now, in this slide, the constraints on primordial black holes are summarized, where here on the y-axis we have the fraction that primordial black holes can make up the dark matter spectrum. And on the x-axis we have the mass in solar mass here on top. And in this work we are mostly interested in masses around mass window C, where the constraints are about 1%. So we consider various models with mass numbers m, which is the primordial black hole mass in solar mass, ranging from 1% to about 1,000 solar mass, with most emphasis put on the low mass models. And we have a mass fraction parameter f, which is the mass fraction of all matter, ranging from 0.01% to 1%. And the third parameter that is of importance is the binarity of the primordial black holes in the Milky Way dark matter halo, which is characterized by eta naught. And hence we can estimate the number of primordial black hole binaries currently residing in the Milky Way dark matter halo, which can be estimated in the following way. And part of this work, part of the goal of this work is to estimate how eta naught differs, how eta naught depends on parameters m and f. So we initialize our PBHs directly after inflation in a Poissonian way. So the nearest neighbor distance xi is modeled in the following manner, where n is the co-moving number density of the primordial black holes. And in what follows, we shift from xi to the lambda parameter defined in the following way. So that's one of our initialization parameters. The other one is the initial angular momentum of the primordial black holes, which we model with a dimensionless parameter j, defined as follows, where L is the angular momentum of the primordial black hole. And what we say is that the primordial black hole directly after inflation gets its angular momentum in two ways. One is from effects of other primordial black holes that surround it, and this is modeled in the following manner, with the typical JF given as proportional to lambda and the mass fraction parameter f. And the second process is angular momentum accretion from the smooth matter component in the universe, which is modeled as a Gaussian in this manner. And these two processes are assumed to be independent, which is a valid assumption in the regime where f is much smaller than 1. And since we limit ourselves to f maximum 1%, this approximation makes sense. Now, binary formation is modeled in a Newtonian approximation, where R is the physical separation between two primordial black holes. We have the Hubble drag here in the linear term, and the gravitational attraction is given as follows. And here we have an angular momentum barrier that is incorporated into the model, which might prevent binary formation at later times since J can grow with time. I'll come back to that in the next slide. Now, binaries form once they decouple from Hubble flow, which means R dot is 0. And at that time, they have a given semi-major axis A star. They have a given angular momentum J star, which is related to the eccentricity at binary formation, and the scale factor S, which is normalized to unity at matter radiation equality, is given at S star at binary formation. Now, as I said, J can grow with time, angular momentum, since J scales with the RMS matter variance, and the RMS matter variance scales linearly with a scale factor in matter domination. We incorporate this in a mean field approach by saying that the time dependence of J is given as the following equation, where in radiation domination, which means S is smaller than 1, J is constant and set by the initial value, Ji, and in matter domination, J grows linearly with the scale factor S. Hence, we get the following results for the binary formations as a function of the two parameters lambda and ji. We see the colored part of the phase space forms a binary with scale factor S star given by the color scheme. And we see that the maximum S star is basically 30. Beyond S max is 30, there's no binary formation, since then the angular momentum barrier grows so much that it counteracts gravity such that binaries will not form anymore. And since we see that after S is 1, also binaries will form, we see that incorporating matter domination is very important in this analysis. However, S is 30 is still small enough such that we can suffice with linear analyses. And in black here, we overplotted the initial PDFs as a function of Ji and lambda. And we see that only a small fraction of primordial black holes will ever form a binary, which is incorporated into the fraction eta star. Now, the newly formed PBH binary is said to evolve in two ways. One is via gravitational wave evolution, and the other one is via stellar disruption, which we will come back to in the next slide. But in this plot, I show the effect of gravitational wave evolution, which is modeled via the Peters equations. Here on top, we see in color the semi-major axis, the present-day semi-major axis of the binary. And in the bottom plot, we see the present-day angular momentum of the binary for a model with solar mass black holes, and f is 0.01. And again, the two random parameters ji and lambda on the axes. And we see that everything left of this diagonal line, which is colored in brown, every binary which would have formed there has merged by the present day epoch. And only the part that is in the colored regime still survives as a binary to today, and a small part above this merger line has significantly evolved its orbital parameters. Now we see that basically 90% of the binaries that have formed survive this gravitational wave evolution effect. And we can go to the second evolution effect that we incorporate into a model, which is stellar disruption. Basically, once the binaries end up in the Milky Way dark matter halo, they can encounter stars. And via either ionization or evaporation processes, these stars can disrupt the primordial black hole binary. And we model this in a deterministic way by saying that once the total rate of disruption exceeds the Hubble rate, the soft binary is disrupted. And this is, of course, a location-dependent process, since the disruption rate is depending on the stellar density, which is location-dependent in the Milky Way. So in this figure, we see the result of stellar disruption at 3 different locations in the Milky Way. One is in the bulge, one is in the solar neighborhood, and one is in the halo, as a function of present-day semi-major axis and present-day angular momentum of the binaries. And we see, first of all, that all of the binaries are highly eccentric. Here in black, we plotted the PDF of the binaries, of the present-day binaries, and we see that they are highly eccentric. So that's one characteristic of the binary population. And this tail that we observe is because of the gravitational wave orbital parameter evolution effect. And we expect most of the loud sources to be in this tail, in gravitational wave signal. And we see also that in the bulge, stellar disruption takes away most of the primordial black hole binary population, while in the halo, it has not really any effect, which we can also observe in this figure, where the galactic spatial distributions are shown, where on the left we have the stellar Milky Way distribution, and on the left we have the primordial black hole binary distribution, which is modeled as an NFW profile. plus the stellar disruption effect, which, as we can see, mostly takes place in locations where the stellar density is highest. So now we can come back to the present-day binarity of the primordial black hole binaries, which is basically just the amount of primordial black holes that form a binary in the first place, which is encapsulated in eta star, times the two evolution effects, the one that survive merger and the ones that survive disruption, which is both are larger than 90% in general for our models. And we see that the binarity is mostly a function of F and only a very weak function of mass number M. And on the right-hand side, we can now see the number of primordial black hole binaries that currently reside in the Milky Way dark matter halo as a function of our model parameters F and M. So the only thing that has to be done right now is to construct a gravitational wave background for our highly eccentric primordial black hole binaries, which we have done by defining a effective waveform in frequency space for non-circular highly eccentric binaries, which is given in the following way, where h naught is the circular waveform, and it's adjusted by this square root of gamma, where gamma is defined in the following way, where n is the multiple number in which the highly eccentric binary emits gravitational waves, defined in the following way. Nu naught is the orbital frequency of the binary. Nu n is the frequency in which the binary emits gravitational waves. And these are related by the multiple number n, where for circular sources, n is 2, but here we can have n is even 10 to the 4 or 10 to the 5 because of the high eccentricity of the sources. Now, the energy density in frequency space is defined as the following way. And once we incorporate this effective waveform, we get an expression that's written below, where psi are the orbital parameters of the systems, and r is the spatial coordinate, and here this phi, the spatial and orbital parameter distributions, are the distributions that incorporate stellar disruption and also the whole binary formation and evolution model that we described before. So these are the result of the gravitational wave backgrounds for the different masses given in different colors and the different mass fractions given by the different line styles. And here in black, we show the LISA sensitivity curve, which also incorporates the unresolved background of galactic double white dwarfs, which is given by this bump in the curve. And we see that in general, the backgrounds are below the LISA sensitivity curve, but for solar mass or subsolar mass primordial black holes, they can exceed the DECIGO and BBO experiments that are proposed. However, we have to note that these backgrounds are averaged over both space and orbital parameters, so there might still be some loud sources that individually can be resolved in LISA. And this is what is shown in these graphs, where if you focus on the first graph first, here on the x-axis, we see the critical SNR that one defines above which a binary is defined to be loud. So if, and here on the y-axis, we have the number of loud sources that appear in LISA above the LISA sensitivity curve, also incorporating the unresolved double white dwarf background. So if one takes a critical SNR of 5, for masses about 1 or 0.1, we expect around 100 primordial black hole binaries to be loud enough to be resolved in LISA once F is 1%. If F is 0.1%, this number drops to around 1. While for the other mass models, there basically are no loud sources. And also we see that the the number of loud sources scales with this critical SNR in a power law manner, where the power law index is expected to be 3 once we have a homogeneous distribution in space. But in this case, of course, the primordial black holes trace the Milky Way dark matter halo modulo the stellar disruption. So we have an inhomogeneous sample. And this is also shown on the middle plot, where we see that the M is 1, the solar mass primordial black holes, and the solar mass loud primordial black holes are distributed more widely than the subsolar mass primordial black holes, the M is 0.1 black holes. And this distinction can be visible in the power law index as well, since the farther the loud primordial black holes are distributed, the more inhomogeneous the sample becomes, and hence the more gamma differs from a value of 3, as typical for a homogeneous sample. So this can be a distinctive feature of loud primordial black holes. So in general, it's the spatial nature of the primordial black holes that might characterize them in observations. And here in the third plot, we show the typical eccentricities of the loud primordial black holes, and we see that they are eccentric, but not as eccentric as the general population of primordial black holes, which can be around 0.99 or even much higher. And also in general, as expected, we see that the loud sources appear in the merging tail of the distribution, with coalescence times ranging in around the range 1,000 to 10,000 years. So with this, I leave you with a summary slide, and I look forward to all the questions that you might be having, and I thank you very much for your attention. Thank you.